A naturally aspirated four-cylinder two-stroke marine diesel engine of stroke 0.18 meter, stroke-to-bore ratio 2.3, and running at 20 revs per second develop a torque of 1100 Newton meter, has a mechanical efficiency of 85%. Analysis of the hydrocarbon fuel shows 85% carbon. The jacket water cooling flows at 2.5 meter cube per hour with inlet and outlet temperature of 35 degrees Celsius and 55 degrees respectively. The charge air and exhaust temperature are respectively 25 degrees and 300 degrees Celsius. A. Obtain the indicated mean effective pressure and draw up the energy balance for the engine. Now the hints we have are our LCV is equal to 42,000, our specific heat of gas 1.09, our specific heat of water, that is CP water 4.2, our pressure of air 101 kilopascal, our specific heat of steam 1.85, our gas constant of air 0.302, gamma of air equal to 1.4, volumetric efficiency is equal to 90%, and our that is supposed to be indicated specific fuel consumption ISFC 0.156. So let's start solving. Okay, from our question we got that our S is, which is number of cylinders, is 4. It's a two-stroke engine, therefore K will be equal to 1. The length was given as 0.18 meters, and our bore to stroke ratio is 2 over 3. We know that the bore is your D and your stroke is your length. So the bore to stroke, that is L over D ratio, is equal to 2 over 3. Now we have D over L is equal to 2 over 3. We're making D the subject of formula since we already have L. So we say D is equal to 2L over 3. So we use that 2 times our L, which is 0.18 over 3 to give you 0.12 meters. Now they said the speed of the engine is 20 revs per second and our torque was given as 1100 Newton meter. Mind you, when solving engine performance analysis, always solve for your torque in kilo Newton per meter. So we're dividing this by 1000 to give you 1.1 kilonewton meter. That is what you're going to use to solve here. Your mechanical efficiency was also given as 0.85, and the volumetric flow rate, like this now is the, in the question they said the jacket water flows at this rate. So the volume of water in the engine from your Q in to your Q exhaust, the volume of water flowing through the whole engine is going to be the same. So we have the volume of water is equal to, the volume flow rate of water is equal to 2.5 meter cube per hour. Now, this per hour, remember that most of our solving is going to be in seconds. So we're converting this meter cube per hour to second. So we'll do it divided by 3600 to give you 6.94 times 10 raised to the power minus 4 meter cube per second. Now in the question we're also given that our inlet temperature for the jacket water, that means the water entering the jacket cooling system, was 308 degrees Kelvin. The inlet temperature for our jacket water cooling was 35 degrees Celsius. Converted to Kelvin, that is plus 273 to give you 308 Kelvin. Our outlet temperature for the jacket cooling, that is temperature 2 of water, was 55 degrees Celsius. Converting to Kelvin, that is plus 273 to give you 328 Kelvin. Now, they said the charged air, the temperature of the charged air and the exhaust gases are given as 25 degrees Celsius. Converting to Kelvin give you 293 Kelvin, and your exhaust gas, the temperature of your exhaust gas is now 300 degrees Celsius. Converting to Kelvin, that is 573 Kelvin. From our hints, we're also given that our LCV is 42,000, LCV 42,000, pressure of air 101 kilopascal, gamma of air, this is also known as your, gamma is known as your specific heat ratio. So the gamma of air is equal to 1.4, The specific heat of gas is 1.09, specific heat of steam 1.85, volumetric efficiency is 0.9, specific heat of water is given as 4.2, the specific gas constant for air is given as 0.302, and the indicated specific fuel consumption is given as 0.156. Now, in the question, we were asked to look for the indicated mean effective pressure. The indicated mean effective pressure is your indicated pressure. Now, we are looking for PI, and we know that WI is equal to PI times Planck's, that is Planck's. So from our parameters, we have our S, we have our K, we have our L, we have our D, we have our N. We can find Planck's. Now, if we go back to this, making PI subject of formula, we're going to divide both sides by Planck to give you PI is equal to WI, that is indicated power over Planck's. Now, we don't have our indicated power, but in the question, we were given our torque, and we know that torque coupled with your engine speed can be used to find your brake power with the relationship formula of your brake power is equal to your 2 pi n torque. So we can get our brake power from this question, from the parameters given. We will now say, recall that your mechanical efficiency is equal to your brake power over your indicated power, and in the parameters we were given our mechanical efficiency to be 0.85. so we can now say we have our mechanical efficiency, we have our brake power, we are looking for our indicated power to use and solve for PI. So we're going to make indicated power the subject of formula here. So making indicated power the subject of formula, we're going to have indicated power is equal to brake power over your mechanical efficiency. So we have our brake power that we've already solved for, which is going back here, we have 2 pi n t. Okay, so we said our brake power is equal to 2 pi n t, 2 times pi, your n which was given as 20, times your torque. Remember I said your torque, you're taking it in kilonewton meter, which is equal to, so our brake power is going to be equal to 138 kilowatts. Now we go back to here where we have our indicated power is equal to your brake power divided by your mechanical efficiency, which will give you brake power, which is 138 over your mechanical efficiency, which is 0.85, to give you 162.4 kilowatts. Now we can put this into our previous formula where we'd say indicated pressure is equal to indicated power over Planck's. So we'll solve that, and we have 164.4 divided by your L times your area, which is pi d square over 4, times your n times your k times your s. Your answer will give you 997.2 kilopascals. Now the next part of the question tells you draw up your energy balance equation. Now the energy balance equation depends on. Okay, so for the next part we have the energy balance, drawing up the energy balance, and we know that our energy balance equation is equal to your Q in minus your charged cool air, the quantity of heat at your charged cool air minus the quantity of heat at your lube oil minus quantity at the jacket water cooling minus the quantity at your turbocharger minus the quantity of heat at your exhaust gases minus your quantity of heat at your residuary heat energy minus your brake power equals to 0. But in the question we were only given the inlet and outlet temperatures for the jacket water cooling. Therefore we are only going to add our Q in, which will always be there, your Q in will always be there, your exhaust gas will always be there, your residuary heat energy will always be there, and your brake power will always be there. So since we're only giving the inlet and outlet temperatures for our jacket cooling water, we're going to add that here. So now we have our Q in minus the jacket cooling water minus the heat transfer into exhaust gases minus the residuary heat energy minus your break power is equal to 0. We're going to have to find each of the quantity of heat at each point here. So let's go to, for finding Q in, we know that Q in has a formula of MF times LCV. So we don't have our MF. To get our MF, we remember that we were given our indicated specific fuel consumption. And we also found our indicated power. So we can say that indicated specific fuel consumption is equal to MF times 3600 over indicated power. Making MF subject to formula, we're going to have SFC times indicated power over 3600. That is going to give us 7.04 times 10 raised to the power minus 3 kilograms per second. Now we have our Q in. So remember, Q in is equal to your MF times your LCV. Our MF is 7.04 times 3 times 10 raised to the power minus 3 times our LCV, which is 42,000, to give us our Q in is equal to 295.7 kilojoules per second. So now let's go and look for our QJ. So go back, finding QJ. QJ has a formula of MW, that is the mass of water, or the mass flow rate of water, times the specific heat of water, open brackets, the temperature at its outlet minus the temperature at its inlet. That is T2 minus T1. So now, we don't have our mass of water. Our specific heat of water was given. Our temperature, outlet and inlet were given. So we're trying to look for MW. We can now say, to get the mass of water, recall from our previous solvings that we can write M is equal to density times the volume. And now our mass of water, we will now say our mass of water is equal to the density of water times the volume of water. And we know that our standard density of water is 1000 times the volume of water that was given in the question, 6.9 times 10 raised to the power minus 4. This volume of water was given in the question beforehand, so you have to check. For those of you who might not know where it comes from, this volume of water was given in the question before. If you go through it, is equal to 0.694 kilograms per second. Now, we put it back into our equation for QJ, saying QJ is equal to MW, which is this. This is our MW, times your CPW, times your open brackets, T2 minus T1. This is your formula for QJ. It's your mass of water times your specific heat of water times your temperature 2 minus your temperature 1 is equal to 58.96296 kilojoules per second. So we have our QJ, we have our Q in. So now let's find our QG, that is the temperature at exhaust gases. So now the energy transfer at exhaust gases has a formula of, if you recall from the previous video I made on energy balance, energy transfer through exhaust gases has two formulas, which is the first one being mg CPG, mg times CPG times TG minus ma times CPA times TA. If steam is added in the question, that equation becomes this, which is mg times CPG times T plus ms, which is mass of steam, times Cp of steam times the temperature of steam, minus Ma times the Cpa times temperature A. Now, some of you may be asking, how do you know if steam is included? If we go back to our parameters, we can see that the Cp of steam was given, so we know that steam is going to be involved in this question. So let's define our parameters here. We have, this is our mass of gas, this is our specific heat of gas which was given, our temperature of gas was given, and temperature of gas and temperature of steam are going to be the same, so we can say Tg is equal to Ts. Mass of steam wasn't given. The specific heat of steam was given in our parameters, minus the mass of air. The mass of air wasn't given. Our Cp of air was not given, but our temperature of air was given in our parameters. So what we are looking for right now is we have to find the mass of air, the mass of steam, the mass of gas, and the Cp of air. Now let's say to get the mass of air, we know that m is equal to density times volume, where density can be written as P over RT. So this pressure of air over the R of air times the T of air, that is pressure of air over gas constant of air times the temperature of air times the volume of air. We don't have our volume of air. We don't have our volume of air. So we can say to get the volume of air, we recall that in our parameters, the volumetric efficiency was given, and we know our volumetric efficiency is equal to the volume of air over the swept volume. The swept volume, which is equal to Lanks, LANKS, Lanks. So we can now make VA subject to formula by cross multiplying, and we have VA is equal to VS times your volumetric efficiency. So handling our VS, which is, handling our volumetric efficiency, which is 0.9, 90%, 0.9 times your VS, which is your L times your A times your N times your K times your S, give you 0.147 meter cube per second. So we can put this as your volume of air into this equation above here, which is your pressure of air over your gas constant of air times your temperature of air times your volume of air. So we go down, which our pressure of air was given in the question as 101.3. Our gas constant of air was also given as 0.302 times the temperature of air, which was also given 298 times the volume of air that you just found here. You bring it here and you solve, you're going to have your mass of air is equal to 0.166 kilogram per second. So we have our mass of air. The next thing we are going to find is our mass of steam. Let's find our mass of steam, or we are going to find our CPA, that is the specific heat of air. So looking for the specific heat of air, when solving, you don't need to write all of this, but it explains how we arrived at this answer. So we can say that, recall that Cp minus Cv is equal to R. Now, the specific heat ratio, which is gamma, is equal to Cp over Cv. If we are trying to make Cv the subject of formula here, we'll cross multiply, we'll have Cv is equal to Cp over gamma. Substitute the value for Cv into this first equation here. So let's call this equation 1. Substitute the value for Cv into equation 1. So wherever you see Cv, you're going to write Cp over gamma. So let's write it that R is equal to Cp, which is this Cp, minus Cv. But instead of Cv, we're writing Cp over gamma, so it's Cp over gamma. Now we're going to make both of them share the same denominator. That is gamma Cp minus Cp all over gamma. You can still call it like terms and rewrite it as Cp open bracket gamma minus 1 all over gamma. Now we're trying to make Cp subject to formula since we are looking for our CPA. So making Cp subject to formula, you cross multiply, you're going to have Cp open bracket gamma minus 1 is equal to gamma times R. Divide both sides by gamma minus 1, you're going to have Cp is equal to gamma times R over gamma minus 1. So assume, if we're looking for the specific heat of air, this is going to be specific heat of air is equal to the gamma of air times the R of air all over the gamma of air minus 1. That's what we did here. The gamma of air, that is gamma A times Ra all over gamma A minus 1 equal to 1.4 minus 0.302. 1.4 minus 1 will give you 1.057. So we have our CPA. Okay, so we can say that, recall from the question, they said the analysis of the hydrocarbon gave us carbon 85%. We know that a fuel is a hydrocarbon, meaning that it's made of carbon and hydrogen. So if out of the fuel, 85% is carbon, that means the remaining percentage will definitely be hydrogen. So we can now say, to get the percentage of hydrogen, we'll do hydrogen is equal to 100 minus 85 to give us 15%, or 0.3. We can now say the mass of hydrogen is equal to the percentage of hydrogen times the mass of fuel. And we have already found our mass of fuel. So we do our percentage of hydrogen times the mass of fuel to give us the mass of hydrogen, which is 1.056 times 10 raised to the power minus 3 kilograms per second. And the mass of steam has a constant formula of 9 times the mass of hydrogen. The constant formula for mass of steam is 9 times the mass of hydrogen. That is 9 times the answer you get for your mass of hydrogen, which will give you 9.504 times 10 raised to the power minus 3 kilograms per second. So now we have our mass of steam. The only thing left is our mass of gas, and our mass of gas is simply the mass of air plus the mass of fuel. We have our mass of air from previous solvings, which is 0.166 plus 7.04 times 10 raised to the power minus 3. This is our mass of fuel, to give you 0.17304 kilograms per second. So we can put all the values we've gotten into our QG formula. Okay, so to find our QG, we put all our known parameters that we've solved for, which is mg, cpg, tg, plus ms, cps, ts, close brackets, minus ma, cpa, ta. So we put all our known values into the bracket and solve to give us 65.9 kilojoules per second. Now, when they say draw the energy balance, we are drawing a Sankey diagram, and the Sankey diagram works with percentage. So to get our percentages, we're going to take all our values we found and divide them by our Q in, because our Q in is our inputs, the amount of heat that actually, like the amount of heat that is input into the system. And the Sankey diagram displays how this heat is separated, or how it branches out. So to get the spread or the separation, we're going to do our whatever we get divided by our Q in to give you the percentage that it breaks off into. So we have our Qj is equal to your value for your Qj over your Q in to give you 20%. Your Qg is equal to value for your Qg over your Q in will give you 25.4%. Your Q in over Q in is going to be 1, that is 100%. I'll show you how to input this in your diagram. Your brake power is going to be equal to, your brake power's percentage is going to be equal to your brake power over your Q in, will give you 47%. Now we have everything except for our QR. Now we have the percentage for all of these. So what we're simply going to do is Q in minus Qj minus Qg minus Qr minus Wb. We're going to make Qr the subject of formula to give you Qr is equal to Q in minus your Qj minus your Qg minus your Wb. Put all their percentages in, and we're going to have 7.6. So your Sankey diagram is just you. Your Sankey diagram is basically just you drawing. This is your base. This Q in, this large space here represents your inputs, and this is where the heat energy splits off, which is here. This is your WB, the percentage for WB. This is your percentage for QG, percentage for QJ, and your percentage for QR. You can decide to make it, since the percentage here is small, you can decide to make this part smaller. This part might be bigger. It's left to your discretion.